My name's Lee, and today we're going to be dealing with some important topics. The topics are inequalities, which of course you did in your grade 11 year, and I'm sure you know that that's something that teachers like to ask, and linear programming, which you also started in your grade 11 year, but there's actually a continuation into your grade 12 year. Now, what I'm going to do is I'm going to recap it right from the beginning so you can understand all the nuances of the section. So let's just talk a little bit about inequalities. Okay, now inequalities are easy enough when we've got something straightforward like this. So say I say to you, solve for x. Now, we know that the first thing we would do is we would isolate the x. So we'd go 2x is greater than, and we are going to transpose that. So it's going to be 3 plus 1, which means 2x is greater than 4. Which means now we have two x's, so we want only one x, so we need to divide this side by 2 and this side by 2 and get x is greater than 2. Now I know you're saying to yourself, well, what's different to our equations? Well, there's absolutely no difference yet. There is a slight problem which I'm going to deal with in a moment. So just be aware that yes, they do work exactly like an equation, but one has to be aware that there is a slight difference when we're dealing with an inequality. Let's look at a problem area. Let's say I say solve for x, and I give you something like this. Right, now we want to isolate the x, so we're going to leave the minus x behind, and we're going to transpose the 1. So if we do that, it's going to be 7 minus 1, so minus x is greater than 6. Now yes, we don't want to know about minus x, we want to know about plus x. So effectively what we're going to do is we're going to divide by minus 1. Now, the moment we do that, there's a complication with the inequality sign. So let's have a look at it. Let's say, for example, I've got 3 is greater than 2. We all know that that's true. And we don't have a problem with that. But now, if I times both sides of this by, say, 4, will it still be true? Well, let's see. Multiplying by 4, 4 times 3 gives me 12, and 4 times 2 gives me 8. Yes, it's still true that 12 is greater than 8. Now, what would happen if I divided by 2? So if I take this thing that's true, and I'm going to divide it by 2, well, 12 divided by 2 gives me 6. And 8 divided by 2 gives me 4. Then, do you agree with me? It's still true that it's greater than. All right, let's go to this case. If I've got 3 greater than 2, and this time I times by negative 4. Let's see what happens. Well, I say negative 4 times 3 gives me minus 12, and negative 4 times 2 is going to give me negative 8. Is it true that that's greater than? No, it's not. That is actually smaller than. So in multiplying by a negative, we reverse the inequality. Now this is something the teachers have been nagging you about, I'm sure, for a long, long time. So okay, let's have a look. What happens now if I divide by minus 2? Well, if I take minus 12 and I divide by minus 2, I'm going to get 6. And if I take minus 8 and I divide by minus 2, I'm going to get 4. Now, is it true that 6 is smaller than 4? No, it's not. It's actually greater than 4. So you can see that whenever I am dividing or multiplying by a negative number, my inequality reverses. And one must remember this all the way through your mathematics, because there's never an exception to that rule. Right, so let's go back to the question we were working with and see how it affects our answer. Well, over here, as I said, as soon as we divide by a negative, the inequality reverses. So in actual fact, x is smaller than minus 6. Now you might say to me, well, how do you know that that's true? It's all very well saying that's working, but let's see if there's another way we could have solved this particular question. Let's say I have 1 minus x greater than 7. Now this time I decide that I don't want to work with a negative x. So let's rather move the x over to the other side so that x is positive. So what we could do is we could go 1. We can transpose that 7 over as minus 7. and we can transpose that over as a plus x. So we have minus 6 greater than x. Is that not the same answer as that? And yes, it is, because remember, mathematics, we can read left to right or right to left. It really doesn't matter. So if I'm reading it this way, it's actually reading x smaller than minus 6, which is precisely that answer. So yes, we can see by solving it a slightly different way that in fact that changing or reversing the inequality is important and actually does give you the correct solution. All right, but now what am I sort of drilling here? Well, I'm not getting too carried away here. I want to now move on to these ones. Say I gave you something like that. Now, if we're looking at x squared minus 1, our instinct, if we're going to isolate the x, is to do this. Now, what do? Can we just simply square root both sides? And the answer is no, we can't. Because in actual fact, that inequality will cause complications. So what we do instead is when we see it is a quadratic inequality, we keep all the things to one side. We make sure we've got a 0 on that side. So once we're here with this x squared minus 1 greater than 0, our next step would be to factorize the expression fully. So to do that, we're going to say this is x minus 1, x plus 1 greater than 0. Now, if I've got two things multiplied together and they're greater than 0, there are two possibilities here. The one possibility that is that a plus times a plus, and the other possibility is that it's a minus times a minus. Either way, my answer would end up positive. And you agree with me, greater than 0 actually means positive. So I'm saying that these two things multiplied together must give me greater than 0. Now, at this point, there are probably about 5 or 6 methods we can use to solve this. I'm going to show you 2 of them, but as I say, there are many others, and probably maybe you've seen one that's different, and that's fine. If you're happy with it and you're working well with it, don't change what isn't broken, leave it as it is. But what I would suggest, if you are using a different method to me while we're solving these inequalities, you use your method and you see if you agree with the answer I get, and then you know you're fine. If not, try to take in what I'm showing you and swap your method, because if you're not understanding what you're doing, rather make a change now. Right, so let's have a look at the first method. The first method is we draw a number line. And we say, let's find our critical, let's just bring the screen up a bit, critical values. Now, what do I mean by the word critical value? Now, basically, a critical value is where the factor would equal 0. So now the factor of this is x minus 1. So x minus 1 equals 0, and the other factor is x plus 1 equals 0. So my critical values will be 1 and minus 1. Now, of course, this working we never normally show. We just do that in our heads and we put it on the number line straight away. But there's no rule that says you couldn't do this as rough work somewhere or another if you prefer to do that. Right, so now we go to the number line. And the one that happens first is the minus 1. And the one that happens second is the plus 1. Right, now once we're here, we do a testing of values. So we go along here and we say, let's choose a number. Let's take another color so we can see. A number smaller than minus 1. Well, if I think about it, minus 3 is a good one. So let's use minus 3. We go over here and we say minus 3 minus 1 is going to be a negative answer. And minus 3 plus 1 is also going to be a negative answer. So a negative times a negative is a positive. We know over here the answer will be 0 because that's a critical value. And if that one's 0, that times that will be 0 as well. Now, let's choose a value between these two. Between minus 1 and 1, 0 is a good choice. You could take a half or negative a half or anything you want to. But I'd choose 0 because it's easy to work with. So if I put 0 in there, I'm going to get 0 minus 1, which is minus, and 0 plus 1, which is a plus. And a minus times a plus is a minus. Right, over here, we choose a value bigger than 1. So let's be ridiculous. Let's choose 300, because it really doesn't matter. As long as it's bigger than 1, I can choose it. So if I take 300, 300 minus 1 will be a positive, and 300 plus 1 will also be a positive. And a positive times a positive is a positive. Right, so what do I want? I want greater than 0, which are the positives. So I want this, and I want this. So, do I want to include this? No, because it didn't say equal to, it just said greater than 0. And I don't want to include this, but I do want everything else that way. Now, all that's remaining on the question, and we're going to do this a few times now, so those of you that didn't understand it, we're going to get another run at it shortly. Now, all I have to do is write the answer. Now, this is interesting because some people prefer to write it in set notation and others prefer interval notation. So just for convenience, I'll do both and you can decide which one you prefer. If you're doing the set notation, you would say x is smaller than, because the arrow is pointing this way, -1, or x is, and this time it's going this way, so it's x greater than 1. That's the form of writing it in set notation. You can also call it set builder notation. Interval notation, you would say where we're starting at minus infinity. Where we're ending up at, we're ending up at -1, and no, careful, you see what I nearly did there, made a nice big mistake. Right, so let's have a look. What we're doing there is we're saying we're going to -1, but we're not including -1. Now remember, a square bracket means including, and if you like, it's equivalent to greater than equal to or less than equal to. This one means not including, and it's equivalent to less than or greater than. So that's why it's a round bracket. And now we can use the word or we can use a U, which stands for union. Okay, if we talk about a union of things, we mean putting them together. So I personally would just use the word or. Union and intersection get a little bit dicey at times and you can make a mistake. So stick to or, that way you're quite safe. Right, so here we're going to start at 1 and we're going to end at plus infinity, close the bracket there. All right, so that's your choice. You can either represent it like this or like that. It's really very much your own choice. It's a preference. I'm not going to say which is the better one. I know most of my pupils prefer the second one because they seem to find interval notation easy to handle. I personally prefer the first one, but it's just because I'm more comfortable with that one. But it really doesn't matter. Okay, so let's go and have a look at the kind of questions we can expect. Right, we can also solve this in another way. Let's show you this way. It's actually a very nice way. I don't know if pupils agree with me because it involves graphs. Now, if we look at this, what type of graph is this? Well, if I wrote y equals x squared minus 1, I'm sure you would all recognize that as a parabola. And in particular, it's a parabola whose axis of symmetry is the y-axis. So we know that if we drew a little quick sketch of this, it would have its axis of symmetry here. Its turning point would be at its y-intercept, which is there, and it would look like this. Cutting here at -1 and 1. How do I know that? Well, I would have said let y equal 0. And if y equaled 0, I would get x squared minus 1, which means I have x minus 1, x plus 1. And if I'm going to solve for that, x is 1 or x is minus 1. So that's how the graph would look. Now, do you agree with me that above here is greater than 0, on the line is equal to 0, and here is less than 0. So if I want to know when is this graph greater than 0, I'm talking about here and here. All right, now if that is the case, there's no problem with the solution because it's going to be everything from there that way and everything from there that way. And you can see that mirrors exactly our solution we got over here like that. So it's actually a very effective way. Of course, that is reliant on your ability to draw the thing you get given. Now, in this case, it was a nice, easy little parabola. We could knock it out in 2 seconds flat. So there is that way that we have available to us as well. And I might mention it again, but I'm probably going to stick to the first way because that is the more traditional way. So, right, you could see that you would just answer x smaller than -1 or x greater than +1. And that would be your solution. Little drawing and that little answer, and we have the question done. Right, let's have a look at some exam questions. These ones have all been taken out of model papers, so you can see exactly what it's about. Let's see the first one. As you can see, I've given it the heading Algebraic Inequalities because we're going to deal with several kinds of inequalities today, and the next time as well we're going to carry on with them. But these are what we call algebraic, because in actual fact we can come up with a completely algebraic solution, no need for graphs, no nothing. So right, let's look at the first question. You see here you have a quadratic. Remember what I said to you? If we see a quadratic, our objective is to get everything to one side and a 0 on the other side. So if you like, effectively, our first step, get a 0 on one side. Now, it's up to you whether you want to move it to the left or the right. But I find from my experience that most pupils prefer to have their 0 on the right-hand side. It just makes it easier for them to tell when it's greater than or less than. They find it more confusing if it's on the other side. So my advice to you is, if you're not worried, that's good. If you are worried, keep to one way. And even if you have to do some maneuvering, like you'll see I'll do now, it's actually worth it because you're not going to go wrong. Right, let's have a look at this. We have 20 plus 3x smaller than or equal to 2x squared. Now, what did I say? Get a 0 on one side, and I said most pupils prefer the 0 on the right-hand side, which means I'm going to go minus 2x squared, because I'm going to transpose that over, plus 3x plus 20 less than or equal to 0. Now, there's a negative there, and we don't like having a negative on our x squared. It's hard to factorize. So what did we have as a rule right in the beginning? We said if we ever multiply or divide by a negative, we have to reverse our inequality. So let's do that. Let's pick another color, and let's do just that. So if we times in by negative 1, we're going to get 2x squared minus 3x minus 20, and this is going to reverse to greater than or equal to 0. Of course, if you didn't do that, the whole question would go wrong then, because you would, well, not the whole question, you would get some part marks, but you would lose the actual end part effectively, because you'll have your selection of your answers, the wrong answers. Right, so now what do we do next? The next thing we do is we factorize. So if you like, our step 2 is factorize. Right, so we've got a 2x and an x, and you can choose any method of factorizing you want. Most of you have probably seen this, and I have shown you on other occasions another way to do it, so it's really your choice. Now, if we're looking for 3, let's try 4 and 5. 4 here, 5 here, and it looks like I've hit it lucky. 2 times 4 is 8. 1 times 5 is 5. If I subtract these, if that's a minus and that's a plus, I will get minus 3. So that looks good to me. So that'll be the minus, and that'll be the plus. We'll put the x's in here. That's a pair, and that's a pair. So we have 2x plus 5, x minus 4, greater than or equal to 0. Right, so now what's the next step? Step 3 is let's find our critical values. Now remember how I said we get our critical values. We take our factors, we put them equal to 0, and we solve them. So effectively here, I'm saying 2x plus 5 equals 0. And if I take 2x plus 5 equals 0, it will be 2x equals minus 5, which means x is minus 5 over 2. Just so you can see it done literally, and of course there's nothing wrong with doing this on the side somewhere. We're going to get 2x equals minus 5, which means x is minus 5 over 2, which, do you agree with me, is actually minus 2.5. Let's just raise the screen a bit. All right, so that's that one, and this one's easy. It's going to be 4. So we draw our number line. We have minus 5 over 2, which, as I said to you, is 2.5. And we have 4. Okay, now it's up to you. Some people find it hard to actually imagine that number, so it's easier to think like this. But if you don't mind, then that one's perfectly good. Dolly, I always call them Dolly Partons because they're top heavy, are always actually good fractions to have. So right, let's have a look over here. Let's choose a value less than minus 2.5. So let us choose minus 7, shall we? Because that's a nice, decent number. So 2 times minus 7 is minus 14. Minus 14 plus 5 is going to be a negative. And minus 7 minus 4 is equal to minus 11. And that's going to give me a positive. Right, between here and here, let's choose any number we fancy. And again, I think I would choose 0. 0 is easy to work with. So 2 times 0 plus 5 is a positive. And 0 minus 4 is a negative. And so this is a minus. This side, let's choose 5. It's a nice convenient number. 2 times 5 is 10. 10 plus 5 is 15. It's a positive. And 5 minus 4 is a positive. And so a positive times a positive is a positive. Right, what are we selecting here? Well, we want the zeros. So we want to include this and include this. And we want the positives. So we want here and here. Now, believe it or not, this is part of the solution. So we make that a solid dot like this and a solid dot like this because we want to include these n bits. Okay. So you have to show some kind of method. You can't just produce this answer. And this is the thing, you can either draw that graph I showed you earlier or this. But there has to be something that helps the examiner to understand how you made sense of this question. Right, so how do we write it? We say it's x. The arrow is pointing this way, so it's smaller than equal to minus 5 over 2. Or you can say x is greater than equal to 4 because the arrow is pointing that way. If you want the other notation, it's minus infinity to minus 5 over 2 square bracket, or square bracket 4 to plus infinity. Just a little warning when you're using this notation. You must always make sure that you put the smaller number on the left and the bigger number on the right. If it's the wrong way around, your interval notation is incorrect. So just be aware of that. Whatever you do, smaller number on the left, bigger number on the right. All right, so let's go now and see how the other one is. The other one says 2x squared minus 6x smaller than equal to minus 4. So I think for convenience, let's pick this up and drag it down so that we can actually have a look at it at the bottom here. All right. Okay. Right, what's your first step? Your first step is to get a 0 on one side. We've decided for convenience, we're going to always make it our right-hand side, but it really doesn't have to be, as I've said, just a good thing to do always consistently. So right, we're going to say 2x squared minus 6x plus 4 less than equal to 0. Now, I can see that there's a 2 common here. You don't have to take it out, but it is a good idea. That way it makes your factorization much easier. And the best way to do this is because there's a 0 here, you divide through by it. So you're going to say 2 into this, 2 into this, 2 into this, and 2 into this. So it's actually gone. So you have x squared minus 3x plus 2 less than equal to 0. Right, what is your step 2? Your step 2 is let's factorize it. So we factorize. And this is a lovely one to factorize, nice and simple. 2 and 1, a minus and a minus. And we now get our critical values. Critical values are 1 and 2. Right, let's test. Let's choose this side of 1. Let's take 0. If I take 0, I'm going to get a minus, and here a minus, so it's going to be a plus. Between these two, let's take 1.5. If I take 1.5, that'll be a negative, and 1.5, that'll be a positive. So we have an overall negative. And over here, let's take 3. And if I try 3, that'll be a plus, and that'll be a plus, so that's overall a plus. Right, what do we want? We want smaller than equal to, so we want to include these points, and smaller than equal to would mean everything in between. So, including, and everything here. Okay, how do we write that solution? Now, with a set notation, to write this solution, the best way is to put your x in the middle, your crocodile mouths, or whatever you call them, your inequalities like that, always facing this way, the smaller number this side, and the bigger number that side. And that's how easy it is to get that. Or the interval notation, which then does become a little bit easier. I'm just going to write it like this. This means x an element of 1 to 2. The reason I do that is sometimes if you've just got a solution like this, is that a coordinate or is that actually an interval? So the moment you put x an element, it makes it clear it's an interval. Okay, so it's just really to make sure that everyone is clear what I'm doing. This case, it didn't really matter because it was a square bracket and we don't write coordinates with square brackets. All right, let's take that off. And so that's the end of that solution. Really relatively easy, I'm sure you would agree. Let's look at the next one. Right, these two, a little bit more exciting. You may notice that over here, we've got something times something less than 6. No good, because this has to be a 0. So, what's your first step? Your first step is to get a 0 on one side. So, effectively what I would do is I'd go x minus 1, x minus 2, minus 6 less than 0. The second step is to factorize. Now, as it stands, we can't factorize this thing. So what we're going to do is we're going to multiply out, add like terms, and then refactorize it. Because at the moment, it is not factorized with that 6 sitting there. So if we're going to FOIL this out, we're going to say that one times that one is x squared. This one times this one is minus 2x. This time times this one is minus x. And that multiplied by that is plus 2 minus 6 less than 0. So we have x squared minus 3x minus 4 less than 0. All right, now it's easy enough. We're going to factorize it. Again, it's not bad factorizing. It's x and x, 4 and 1, a minus and a plus. And now we're going to get our critical values. You see how I'm starting to just go a little bit faster, not writing down all the steps. Eventually you, if you practice enough, will certainly be able to do that just as easily. So, right, over here, we know that the one critical value is 4, and the other critical value is minus 1. Remember, they must be placed on a number line, so the order is very important. You've got to have the smaller one and then the bigger one. You can't mix that up. Right, so let's choose a value this side of the minus 1. Let's take minus 2. If I put in minus 2, let's change the pen so you can see the substitution happening. If we take a minus 2, it's going to be a minus. And a minus 2 plus 1 is going to be a minus. So that's a plus. And over here, if we choose a value between these two, let's take 0. We're going to get a minus times a plus, which is a minus. And over here, let's take 5. And if we take 5, it'll be a plus times a plus, which is a plus. And now we choose our solution. So we want smaller than 0. So we want the negative. So it's here. Do you agree with me? We don't want to include those endpoints. So when I write it up, I'm going to have open circle, everything between. Now, this is a good case of where that x and element is useful if you're using the set builder notation the interval notation form of writing that up. Selector, you're going to go x. We're going to sandwich it. We're not including either end, minus 1 to 4. Or we can go x and element, round bracket minus 1 to 4 round bracket. And that's that question done. Not a bad one to do. Let's look at the next one, the B1. And the B1 looks as follows. It says that x squared minus 8 times x minus 2 greater than 2. Do you agree with me that in actual fact it's much the same process? So let's do it alongside here. And let's put a line in here. And that was the A. And let's call this now the B. So right, the first thing we do is we get a 0 on one side. The next thing we do, we would get it into a form that we can factorize. So that means I have to multiply this in. So it's minus 8x plus 16 minus 25 greater than 0. So it's going to be x squared minus 8x. And if I add those two, I'm going to get minus 9 greater than 0. Factorizing, fortunately again, very easy to factorize. X and x, 9 and 1, a minus and a plus. And our critical values then are minus 1 and 9. Right, so far exactly the same procedure, even though it looked slightly different to the first one. The method or the technique we're using is not changing. So it's all good. Right, so over here we go and we try something smaller than minus 1. Let's take minus 2. It'll be a negative times a negative, which is a positive. Between these two, let's take a 0. It'll be a minus times a plus, which is a minus. And this side, let's take 10. It'll be a plus times a plus, which is a plus. Right, what are we selecting? we are selecting greater than 0, so we want here and here. We do not want that value because it's only greater than, not greater than equal to. So that's our solution we want. So it would be x smaller than -1 or x greater than 9. Or if you want to use other notation, minus infinity to -1, round bracket, or round bracket 9 to plus infinity. And here I think it's clear enough. You wouldn't have infinity in a coordinate, so you wouldn't have to write the x in element to be sure your examiner understands what you're doing. Right, let's look at the next one. Okay, and here you can see I'm giving you something that looks a little bit different. Not hugely different, but a little bit different. Right, now, do you see that there is already a 0 on one side? Wonderful. And do you see that it's already factorized? Maybe not fully factorized, but factorized. Because this is a factor. This here, can this go any further? And the answer is no. X squared minus 9 cannot be factorized further. If it had been 2x minus 1 times x squared minus 9, well, then you would have carried on. You would have gone 2x minus 1, x minus 3, x plus 3, smaller than 0. And if that had been the case, you would have then had 3 critical values. You would have had a half, 3, and minus 3. Would that have made a difference in your life? The answer is no. All it means is you have to test more often. But really, the number line would go in just like before. There would be the -3, the half, and the 3, and we would test. In fact, let's just do this since I've got it up here. Let's quickly just look at how it would work if it had 3 critical values. Right, so if we choose a value this side of -3, let's take -4. If I put it in there, it's going to be a negative. If I put it in here, it's going to be a negative. And if I put -4 in there, it's going to be a negative. So negative, negative, negative makes a negative. Let's choose between these two. Let's take 0. If I take 0, that's a minus, and a plus. So that's going to be a plus. And over here, if I choose between these, let's take 1. It's going to be a positive, a negative, and a positive. So overall, a negative. This side, let's take, say, 4. If I take 4, it's going to be a positive, and a positive, which is a positive. And if I want to select here, I want smaller than 0. So I want these and these. Okay, do you agree with me? I would not be including those points because it only wants smaller than. So I would write x smaller than -3 or x sandwiched between a half and 3. And you're also welcome to use the other notation if you prefer. Right, so if there were 3, it really would make no difference to your method. It would take you a bit longer because you'd have to test more often. But it's really not a problem area. Let's have a look at this here. Right, so now it's factorized. It's got a 0 on one side. And if we look at it, we can see we will have a critical value. But only one. We'll have the critical value that 2x minus 1 equals 0, which means 2x equals 1, which means x is equal to a half. So there's your only critical value, because do you agree with me, this one here, if I put it equal to 0, would not be able to solve if it was a real number. If it was non-real, that would be fine, but we don't work in non-real at school, so it definitely does not have real solutions. So right, so there's no solution here. So we would draw our number line, pop in our half, and we would still do exactly what we did before. We would test. So let's choose a value this side of a half. Let's take 0. If I put 0 in there, I'm going to have a minus. If I put 0 in there, I'm going to have a plus. So that's a minus. Then if I choose this side, let's take 1. If I take 1, 2 times 1 is 2, minus 1 is 1, so it's a positive. And of course, this is a positive. So overall, this is a plus. What do I want? Well, according to my information, I want smaller than 0, so I want here. So to write that, I would not include this point, and I would do everything this side, so it would be x smaller than a half. Okay, so we can see how it's done. Relatively easy, relatively straightforward. Let me show you just one little complication, which I actually didn't plan on, but I just suddenly thought to myself, let's just show you this. It's actually worth thinking about. I don't know if the teachers would get mean enough to ask this, but you never know, so let's just make sure. Supposing I gave you something like this. All right, so remember the rule is you must have a 0 on one side. Well, we have that. Second step, we must make sure everything is factorized. Well, it's partially factorized, but not fully factorized. Do you agree with me that this would become x minus 3, x plus 3 from that? And this is still x plus 1 squared. I could write that bracket twice, but it really doesn't need to be. Right, so what are my critical values? Again, I'm going to have 3 critical values. I'm going to have minus 3, minus 1, and 3. So minus 3, minus 1, and 3. Remember what I said to you about the order being very important? Well, it is very important. Now, this is equal to, so we know we're going to include these points in the end, but let's leave it at that for now. Let's go and test. Let's choose a value this side of minus 3, minus 5. If I choose minus 5, that'll be a negative. That'll be a negative. And this will be a negative squared. So in actual fact, there's 1, 2, 3, 4 negatives. So overall, we've got a positive. Let's choose this side. Let's bring between those minus 2. If I put minus 2 in there, I've got a negative, a positive. And if I put a negative in there, I'm going to get a negative squared. Now, do you agree with me? I've actually got 3 negatives. 1, 2, 3. So it's overall a negative. Let's choose this side. Let's take 0. So if I take 0, that's a minus, that's a plus, and that's a plus squared. So looking at that, there's only one negative sign, so it's a negative. Ooh, look at that. Bit worrying, but not really that worrying, because you'll see why in a moment. And then we choose this side. Let's take, say, 4. If we take 4, 4 minus 3 is a positive. 4 plus 3 is a positive, and that's a positive squared, so overall that's a positive. Now, what do we want to select? We want to select greater than equal to. So we want the positives and we want the zeros. So we want to include those points as well. Right, so let's make it more clear. So it's solid this way, solid, solid point that way. So we could say x is smaller than equal to minus 3, or x equals minus 1, or x is greater than equal to 3. Okay, so really very straightforward. This is what happens when we have a bracket squared. There's a repetition of sign over that critical value. So if you remember that, you'll never panic if it happens to you, because you'll know, well, that's right, that's what should happen. Okay, if you want to show the other way of writing it, you go minus infinity to minus 3 inclusive, or, and this can't go into interval notation, and this one 3 to infinity. Okay, so that's really your choice, that or that. Right, I think we've revised our grade 11 work relatively well, and we need to now progress to looking at what our inequalities were about in functions. So now we're going to move across to the graph version of this. So let's go here and see what we're doing. Now you can see I've got an axis here, and believe it or not, at the bottom here I've got some equations hiding. It says sketch each of the following graphs on the axis provided, and the first graph is x smaller than equal to 6. Now what I've done is I've actually copied this question 4 times, so each graph will have its own axis. Just makes it so much easier for us to refer to. So we're not going to worry about it too much. We're going to start just with the one, x smaller than equal to 6. Right, let's have a look. The graph is x smaller than or equal to 6. Now, first of all, on an axis, you always mark your origin in, you clearly mark your x-axis and your y-axis. It is not necessary to put arrows on both sides of the line. The program I use does that automatically, so I just left it at that. But in actual fact, you only need one arrow on an axis line. So you could just have this one and say that one. But if you did do both, it doesn't, arrows don't actually necessarily mean continuous forever. It actually implies direction. So strictly speaking, having 2 arrows on a line is confusing. But I know within school contexts, we use it as this continues. All right, so let's have a look at inequalities in the functions. So how would I draw this graph? If I was drawing x equals 6, how would it look? Well, we would go, first of all, we'd mark our axis. So 1, 2, 3, 4, 5, 6. And you don't have to mark in everything, just some of the stuff. Okay, now that's a perfectly respectable axis. So how should we draw this graph? Well, it actually is a special case. If we look at it, it's saying to me that the x is 6 always. So in other words, it must be a special case like this, where it's a vertical line, where it's going through the 6. Now, what is different to what we've been doing before, because that is the graph, we want to do this one. Well, we want to shade or show them where the solutions would be where x is smaller than or equal to 6. Now that's relatively easy on this particular example, because we know that if we're looking at a line like this and we're saying where is it smaller than, well, it must be smaller than where the values are less than 6. So in actual fact, this would be the area I would shade to represent that particular inequality. Now, of course, that can be as untidy or as neat as you like. Mine isn't too tidy, but it's absolutely fine. You can see what I'm making the point of. Right, so let's go to the next one then and see what the second question says. Right, the second question on this list says y greater than minus 2. So y greater than minus 2. Now, do you agree with me? Again, this is a special case. However, we are sketching y equals 2, but if we look over here, they want it greater than 2. They don't want it greater than equal to. So we've got to find a way to represent this graph so we show them that. Well, all we're going to do is we're going to use a dotted line to say, well, here's my barrier. I'm not including it, but I'm including everything either left or right or top or bottom of this particular thing. So let's go and have a look. Let's select a line. And this time I want to sketch this. But before I do that, I think I should mark my axes, actually. Been very bad. There's the origin, there's x, there's y. Let's stick some values in. Of course, your life is made very easy by having some block paper or graph paper to do these kind of things. All right, so back to this. I want to draw y greater than minus 2. So if I was drawing y equals 2, it would have looked like this. Okay. And you can see that now by dotting it, I'm saying, hang on, not this actual line, but I'm now going to decide where I'm going to go from there. So right, let's go across to this. Now it says y greater than. Well, if it's minus 2, what numbers are greater than minus 2? Well, it must be minus 1, 0, 1, 2. So we're actually interested in the section above this line. So there we are. That's how we would represent that solution graphically. Quite simple, quite straightforward. The special cases make it a bit easier. We're about to move now away from special cases to more traditional. And there I'm going to show you some techniques and teach you some little shortcuts that are quite useful at times. Right, let's go to the next one. The next one says, let's sketch y greater than equal to minus 2x plus 4. So y greater than equal to minus 2x plus 4. Now the good news is with this one is they want me to include the line because there's an equal to sign. So in actual fact, I'm going to sketch this graph first of all. Now, how many ways do I have to sketch that? Well, if you remember back from our function lesson where we did some revision, we talked about 3 ways to sketch a straight line. You can, of course, use table method, which is quite a long-winded way. You can use gradient intercept, which is quick and easy, or you can use dual intercept. And quite honestly, I think dual intercept is probably the easiest one. You'll see in the 4th case we can't do that, and then I'll show you what we do. But in this case, we certainly can do it. Now, there's almost like a gimmick I use that is very, very useful. I go to the equation and I say to myself, all right, let's first of all mark these things for ourselves. 1, 2, 3, 4. In fact, I think I'm going to sub-mark it so that it's not such a huge graph. So I'm going to make every half a number. Of course, accuracy is everything here. So try to mark it properly and all that stuff when you're working on these kinds of papers. Right, so if I look at that, I can see that if I take my finger and I block the x, I can see that y had to be 4. So I would go along here, that's 2, that's 4, that's where I'm going to start over here. Then if I go here and I block the y with my finger, and I solve for the x, I can see that the x would equal 2. So I would go over here and do that. Now let's do it properly, and you're going to see when I start doing the real linear programming questions, I often use this technique because it's a quick, simple way to sketch them. But I'll just do it properly here for you. If x is 0, then y is equal to 4, so we have coordinate 0, 4. And if y is 0, then 0 is equal to minus 2x plus 4, which means 2x is 4, which means x is 2, so we have coordinate 2, 0. So you see, doing the dual intercept method the normal way, here I get the values. I just sort of shortcut a little bit. All right, let's get hold of a line and put it in. Okay, I'm going to have to do a little bit of shifting here because my eye wasn't that straight. Okay, that looks pretty much right. Okay, right, so now we're saying to ourselves, that is the line equal to. I want y greater than equal to. Now, how can I be sure where I should shade? Now, there's a proper way to do it, and there's a cheat way to do it. And I'm obviously going to show you the shortcut, but let's start by doing it properly and correctly. We choose any point that is clearly above or below this graph. Now, if I look at it, I can see that the origin, 0, 0, is clearly below. I could have chosen out here, say, 4, 4, which is clearly above, which is also fine. But let's start with 0, 0. I'm going to take this equation, and I'm going to substitute that 0, 0 in for x and y. So 0 is greater than equal to minus 2 times 0 plus 4, which means 0 is greater than equal to 4. Is that a true statement? Well, is 0 greater than or equal to 4? And it clearly is not. So therefore, that cannot be in the solution I want. So by default, if I can't have this solution, I must have this solution. And so I would shade there. Okay. Let's test the 4, 4 just to show you that if I had chosen the 4, 4, it would have worked. Because now I would have got 4 greater than equal to minus 2 times 4 plus 4. So I would have got 4 greater than equal to minus 2 times that is minus 8 plus 4. So 4 greater than equal to minus 4, is that a true statement? Yes. 4 is greater than minus 4, so that's why I would shade that area. So that is if I'd chosen the correct area to shade. So if I choose a point clearly in one side or the other, test it and it defaults, it doesn't work, then I shade the opposite area. If it does work, I shade that area. Now, of course, as I said to you, there has to be a shortcut here. Now, the shortcut's quite easy. If your equation is in y form, which this one is, and it's greater than, you shade above the line. And if it was less than, you would have shaded below the line. But it must be in that format to actually make that decision. Now, that's not a hard thing to do, so that's also all right. And you'll see I'll use that a few times as we work through the section. So don't worry about it. We'll recap this a few more times. All right, let's look at the next one. Right, the fourth one, as I said to you, is not going to allow me to use the dual intercept method. I want to sketch y less than 3x. All right, so let's go here. Well, if I was going to sketch y equals 3x, what would be the best approach? Well, do you agree with me that dual intercept would not work? Because if you let x equal 0, y would be 0, and if you let y equal 0, x would be 0, so you would have one point there. That's it. You wouldn't be able to draw anything. But gradient intercept would work very nicely here because we know that we have y equals mx plus c, and the c is 0. The gradient is 3 over 1, so it's positive, so we're going to go up and to our right. Let's just mark our axis because we need to use that. Okay, x, origin, y. Right, so what am I saying? I'm saying we're starting over here. In fact, let's make it blue so we can see it stand out. There's blue, the naught, and it tells me to go up 3 and 1 across. Now, having done that, I can draw my line. Like that. However, I have ignored the fact that I only want less than. So what I'm going to do rather is lift this line and go back to that and use the dotted line, which is what I have to use if it says less than and not equal to. Right, so let's put the dotted line in. That's a bit better. Okay, so now we have to decide where to shade. If we're using the shortcut that I've shown you a few minutes ago, y is less than 3x. Less than means shade underneath. Shading underneath would be here. But let's test properly. Do you agree with me that this point over here, 3, 1, is clearly at this side of the graph? So let's take the thing and put it in. 1 is less than 3 times 3. So 1 is less than 9. Is that true? Yes, it is. So we shade this area. And there's our region shaded. So just to give you a quick run on that, it's really very simple. It's the graphs we've been drawing since grade 9, and we've added in a little bit of shading of inequalities on the actual function. Now let's go and have a look at a little bit more complicated question. Right, let's look at question 5. It says draw sketch graphs of the following inequalities. They give you two equations, y less than minus 2x and y greater than equal to x minus 3. And then the third part of the question says shade the region common to all the inequalities. Now this is where we start moving into the real linear programming techniques and those kind of like issues around language and all sorts of things, and we'll build it up as we go. So right, let's have a look at it. I think let's move this question down so it's out the way, and let's have a look at each of these graphs. So we're going to do them individually. Let's start with this one over here. Y less than minus 2x. Now we've just discussed in the previous question that if it takes that form, the best approach is to draw it with gradient intercept. So the c value is 0, the gradient is minus 2 over 1, so it's going to go down 2 and 1 to the right. Let's mark the axis in. Now, of course, with these things, it is important that things are very accurately drawn, because often we are going to read off solutions off this axis. I don't think in this one, but certainly later on we will be doing that. And so it is a good practice to actually make sure, if possible, that you are doing things very accurately. And that's your y-axis. Right, so what am I saying? I'm saying I'm starting here, and the gradient is negative 2, so it's down 2, 1 to the right. Right, now because of how it is, let's get a line, and we have to have the dotted line because it's not including those points. So let's put it in. Okay, I might have to do a little bit of maneuvering here, but that's fine, not a problem. So anything when you are not working with a ruler can be exciting sometimes. It makes life look different. Okay, there, it's in the right position now. Let's just stretch it out a bit in case we need some space. Right, now, what happens when I'm representing more than one on a situation? It is a very good idea not to get carried away with your shaders at this stage, but to rather use a subtle way of shading. So let's show you what I mean by a subtle way of shading. This is y less than. So according to the little shortcut rule I've taught you, that means underneath. So that means I'd be talking about this shading. Now if we wanted to make sure we could choose a definite point, let's choose 1, 1. If I put 1, 1 in there, 1 is less than minus 2 times 1. Is 1 less than minus 2? Clearly not. So that point can't be in the region, it must be down here. But if you trust me, and I hope you do at this stage, you'll be able to do that without that. Right, this next one. We have to sketch this, and this one we can deal with dual intercept. Now remember my cheat way. I looked at it and I said if x is 0, y will be minus 3. And if y is 0, x will be 3. You want to do it the proper way, feel free. And this time, it's going to be a solid line. And once again, I need to just do a little bit of creative altering to fit it in. Right, so knowing that, where do I have to shade this? It's in y form, it's y greater than, so I'm going to shade above. See the subtle shading? It's quite nice. It doesn't make your drawing too cluttered. And now we can actually do what the question asked. The question asked, shade the region common to all inequalities. So in other words, you've got to shade where all these arrows are pointing to. Now, if you look at the purple arrows, they are pointing down, and the blue arrows are pointing up. So this is the area that is common to these things. Now, there's one little problem here we need to take into account. We have a dotted line meeting a solid line, which means this coordinate cannot be included. So we have to put an open circle there to tell them that point may not be there. Now, at this stage, I'm going to start talking jargon. I will sum it up a little bit later on, give you nice definitions of what it is. But basically what's going to happen now, are we going to call these things, these lines we're drawing, constraints. This here, this common shaded area, we're going to call the feasible region. So I haven't used that jargon, but in actual fact, you've just used two of the things that happen in our linear programming. So, as I say, it's something we should be quite comfortable with. It's a nice section to do very well in. Right, let's look at the next one. Question 6. It says, graph the solution set of the system and find the coordinates of the vertices of the feasible region. So you see here they're using that word I was using just now. Feasible region is where all the inequalities are satisfied. So it's the common shaded area. Okay, but now they're adding in a new thing, vertices. What are vertices? Well, vertices are where two lines cross each other. That point is a vertex, or vertices for plural. So you might have heard them talk about a vertex, singular, and vertices, plural, but it basically means where two lines would meet. So that would be a vertex. Okay, so that's what we're heading for in a moment. Right, so we are going to look at several graphs. Let's do each one in a different color so we can see what's going on. This is a lovely section if you enjoy making your work look good. I know the boys generally don't, but I enjoy having a nice, neat drawing with clear markings and colors to help me see what I'm doing. Okay, so those are the graphs we are drawing. Let's take the graph down and let's have a look. Now, I think in the light of the fact that this has got an 8 in it, I'm going to mark this in 2s. Okay, to 10. And I'm just going to be a little lazy on the negative one and mark every second one in. But it's fine. I mean, obviously, you're not going to be doing millions of these in an exam. You're going to be doing one. And so it's really not a problem if you have to take a bit of time to do this. There's a problem when you're doing 1,000,001 examples, then it can become an issue. And you'll find that mostly teachers advise you to use block paper or graph paper, and in the exams you're provided with the block or graph paper. Right, so let's look at the first graph. The first graph is x plus 2y greater than equal to 8. Right, so now if I look at that one, I can decide to do it in any of the methods, but I'm again going to use my shortcut. So I'm going to say if x is 0, effectively I block the x off, y would equal 4. And if y is 0, so now I block that off, the x would equal 8. So those 2 points help me to draw that graph, 0, 4, and 8, 0. Okay, I can go and pop that in. Okay, I might have to do a little bit of moving. I think that's pretty much right. You'll find it easier than me to do this because your rulers can be lined up properly. Right, the next one, let's do it in purple. The next one is 2y minus x less than equal to 4. Okay, again, if x is 0, and if y is 0. So if x is 0, I block that up. That means 2y is less than 4, which means y is equal to 2. And if that's 0, x is equal to minus 4. Okay, so now we go over here. We want to plot 0, 2, and minus 4, 0. And we want to draw that. And I think I need that little thing there. And to draw it, I think I'm going to do it in the orange, because I don't have a purple pen handy there. All right, let's do some maneuvering. Okay, right, now before I move on, I want to just go back for 2 seconds and talk about the shading. I didn't mention the shading here. Do you agree with me? This would be 2y greater than equal to minus x plus 8. And if I divide by 2, the y would be there, but it would be greater than. It wouldn't change around. So y greater than means I'm shading above on the blue line. Okay. And then if I look at the purple line, here I've got 2y smaller than x plus 4. So y is smaller than a half x plus 2. And you can see it's smaller than, it's underneath, so I'm shading over here. Now, do you agree with me? At this moment, without putting the third one in, it's clearly that the shading that's common is here in this portion here. All right, let's go and look at the last graph. And I'm just going to erase that so I've got some room to work. Okay, and let's make this one in black. It's 3x minus 2y less than equal to 8. Okay, now this one's not going to produce such lovely numbers, but we're going to do it anyhow. Okay, if x is 0, what is y going to be? Well, I block it up, and I can see that y will be minus 4. Good. So there's the minus 4, plot the point. In fact, that's not a very nice minus 4, so let's just make it look a little bit better. Right, and if y is 0, well, if y is 0, then 3x equals 8, which means x equals 8/3. Now, 8/3 is not a pretty number to write and to plot, but we can still do it. So we're going to go along here. 8/3 is about 2 2/3. So 2 2/3 about here. And we know that our line must go through that. So let's go to the black line. And let's draw it in. Again, I'm going to have to do some maneuvering here. Okay, that looks more or less correct. All right, where are we going to shade for this particular one? Well, we have to tidy it up a little bit. We have minus 2y less than equal to 8 minus 3x. And if we divide by a negative, remember what I said to you, that sign reverses. So it's going to be minus 4 plus 3 over 2x. So we're shading y greater than, so it's above. So we're shading there. And if we look here, where do all our points point? They point into this little area here. Now, what we would do in this situation, and I think I'm just going to clear here so we can see what's going on, and maybe clear here. I don't want it too cluttered. Okay, so this is what we call the feasible region, and what we would do is we would label it using capital letters. So we would go feasible region, and I'd sort of draw a little replica of that. And I would make sure that they knew I was talking about that. Okay, so now having done that all, that's my feasible region. What is the next part of the question? They say, determine the coordinates of the vertices of the feasible region. Now, the vertices of the feasible region are, in fact, that A, B, and C coordinate. Now, if this has been accurately graphed, it is possible to read these straight off the graph paper. And in fact, a lot of the time, that's what they would encourage you to do. But if you have any doubt, rather solve it simultaneously. And that's what I'm going to do to a large extent here. Right, so let's have a look what we can see. I can see this one clearly, C. I'm happy to say this one's coordinate is 4, 2. I'm not so sure about B. A, I sort of have an idea it's 2, 5, but I'm also not that sure about A. So just to be safe, I'm going to solve simultaneously for those two. So now I think you're starting to see what a lovely section this is. Firstly, you're getting to draw your graphs. Secondly, you're using inequalities. Thirdly, you're finding out where the intersection of the inequalities are. And now, heavens above, you've actually got your simultaneous equations. So really a lovely section, lots of nice things to do in it, nice for teachers to ask. Right, so now what we have to do is we have to find a way to solve this. Now what I'd like to suggest to you, and this is something I didn't do here and I'm going to do it right now, what we do is we number our equations. We know that this was equation number 1, this one was equation number 2, and this one was equation number 3. Or alternatively, you have to write the equations on these lines. I personally think it's quite nice to just do what I did. You've numbered them. It's clear to the examiner or to whoever's marking which one is which one, and you can then read it off. Okay, so let's go here. We want to find out what happens when number 2 and number 3 cross each other. So number 2's equation was 2y minus x equals 4, and number 3 was 3x minus 2y equals 8. And we want to solve simultaneously for point C. So to do that, we're going to get our 2y on its own in both of these equations. So let's call this equation 1 and equation 2. From 1, I can say 2y equals 4 plus x. And from 2, I can say 3x minus 8 equals 2y. Now, if they are both equal to 2y, which they are, I can put them equal to each other. So 4 plus x equals 3x minus 8. So that means that 2x is equal to 12 because I've transposed, and that means that x is equal to 6. So we know that this is going to be 6. So you can see my drawing isn't 100% accurate because now I've got a wrong spot there. It isn't quite on the 6. But that's fine. You can see the simultaneous is helping me out. Now I can go back to either equation. So let's go to this one, and it's 4 plus 6. So 2y is equal to 10. So y is equal to 5. So this is the coordinate 5, and that was pretty good. You can see that was more or less correct. So B's coordinate is 6, 5. All right, good. Let's now go and have a look at how we would solve for A. To solve for A, we're using equation 1 and equation 2. Now, you might notice all I've done is I've reshuffled them so that the x's are under the x's, the y's under the y's, and numbers under the numbers. The reason being here, I'd like to show you the elimination method, since I showed you basically a substitution method in the first one. So if I look over here, if I add these, so I take equation 1 and I add equation 2, the x's will fall away, and I will get 4y equals 12, which means y is equal to 3. So we know that the y value of this is 3, and if you look at the drawing, that looks more or less right. And now we can sub into either equation. So let's go into 1. So x plus, so let's just take this up a bit, x plus 2 times 3 is equal to 8. So x is equal to 8 minus 6. So x is equal to 2. So that means this coordinate for A is 2, 3. And we could see the 2. We weren't so sure about the 3. So actually the drawing itself wasn't half bad. It was actually quite solid, and you could actually read off your coordinates pretty well, except for that B one, which wasn't perfect. That was probably caused by the 8/3, which is hard to get accurate. Okay, so have you answered the question? Yes, you have. They wanted the coordinates, and you've given them to them. You say A is 2, 3, B is 6, 5, and C is 4, 2. Are we happy? That's relatively straightforward. Now, at this stage, I'm going to move into proper linear programming and show you the first kind of question we can get. And it's a relatively easy start. Right, just before we do that, I just want to talk a little bit about the jargon. As mentioned earlier on, we talk about constraints. And those are the actual inequalities. Now, just before we move off that, I want to say that there are two kinds of constraints. We have what we call the inherent, and then, if you like, explicit. If you want to use the word implicit here, you can also use that word. But basically what this means is that if we look at this constraint, it's something that happens from the context of the question. So, for example, we are talking about washing machines. Clearly, we're not going to sell 1.5 washing machines. So inherent in it is that they have to be whole numbers. Or perhaps we're talking about, I don't know, cars, any object or people. You can't have half a person. Well, you can, but they won't be alive anymore, which doesn't really help much. But those things are not actually made as part of your things, but you have to bear them in mind and you have to use them, and you're going to see me use them quite often. Now, the explicit ones are the ones that tell you, like the equations I've been giving you and you've been sketching. Right, the feasible region we've talked about already. Let's just give you a quick little summary of that. It's where all the inequalities can be solved. We've talked about vertexes. Another word for them, or vertices rather, plural, is corner points. Now, corner points make it a little bit more explicit. Okay, it's obviously clearly when you've got this little shaded portion of whatever you've got over here, these would be your corner points or your vertices or your vertex, the singular. Right, now we're going to go to something called the objective function. Now, objective, what do you think about when you think about the word objective? Well, objective is where it's not conditional to anything. It's something that you're looking at, and it's independent of. So this thing is the thing we're going to maximize or minimize. And in dealing with this, we are going to deal with 3 different ways of doing it. We're going to talk about using the corner point method, or another name for it is the simplex method. We're going to talk about a search line and optimizing. And lastly, we're going to talk about comparing gradients. Okay, and all of these methods are valid methods, important to know. And if I'm talking about optimization with a search line, I will show you what I mean about it, but there's also something called an optimal position. Now this stuff, as I say, as we go, I will highlight them. Optimal position. In other words, that's where it will maximize or minimize for that particular situation. All right, let's move to the next question. We're going to have to move quite quickly because we're almost out of time. So let's go to this question here and let's look at it. The graphs of the linear programming problem have been shown in the figure below. So you can see there's a drawing. Determine the inequalities, and in fact this is a shaded area. Determine the inequalities which are used to obtain the feasible region in this diagram. Now if we look at that, basically all that is finding equations of straight lines, which you guys are experts at. You've been doing them forever. So let's look. The easy one is this one. If I look at this one here, I can see that's 10, 11, 12, 13, 14, 15. That's 15. So I know that this must be x, and it must involve 15. And I'm shading this side of it, so it's x greater than equal to. So that's the one down. This one's also easy. It's again an x, and this time the value is 40. But this time I'm looking this away, so it's less than equal to 40. This one is also relatively easy. It's a y, and it's involving 5, and we're shading above, so it's greater than equal to. And this one's a 20, and this time we're shading down, so it's less than equal to 20. So those 4, very easy to get hold of, no problem at all. The only hard ones are these 2 here. So let's quickly knock those 2 out, and we can go from there. So now what do we know about those 2? Well, we know that this point E is the coordinate 0, 30. And if we're finding this line here, that coordinate is 60, 0. Now, if we've got 2 coordinates, can we find the equation of that line? Yes, certainly we can. We've got the gradient, easily found, by saying y2 minus y1 over x2 minus x1, which is minus 30 over 60, which is minus a half. And of course we knew the y-intercept. If you go back there, it cut at 30. So we could say y is equal to minus a half x plus 30. But we are asking you to shade underneath, so we make that smaller than equal to. So there's the graph. Very simple, very easy, no problem at all. Right, so now let's look at the last one, which is this one over here. And if we look at this one, it's cutting at 30 and 30, so this is going to be 0, 30, 30, 0. And you can see that the gradient would be minus 1. Hopefully you can see that. Let's show you why. The change in y is 30, the change in x is 30, and it's going negatively, so it's minus. I think we could have done the same here. The change in y is 30, the change in x is 60, and so the gradient is negative a half. Right, so over here, we are going to now go and find the equation, which is y equals minus x plus 30, and we want to show it above, so we're going to do greater than equal to. So there's our second one. All right, I don't want to rush this any further. So I think at this stage we'll stop. We found the equations. Strictly speaking, you should write nice, neat equations out here. And then what we'll do next time is we'll start with this, and we'll start with the objective function. Because the next lesson we're going to continue this and finish this section off properly. Thank you for joining us today, and I hope you've learned a lot of the new things, or revised a lot of new things, and reminded yourself of what you've forgotten. We will see you soon. Goodbye.